All right, so go ahead and submit your response there. Just a fun question because we're going to be looking at these data. No Googling in here, all of you. And so I'm going to just leave that for a minute up there. And as you're getting logged on, the Learning Catalytics session number is over there. I believe I recorded it correctly this time. And then we'll go ahead and start with the announcements, and then I'll come back to this question. Okay. What's that?
Are we graded on this one?
No, we are not graded on this one. It's just a fun question just to see how many of you are sports fans, David Ortiz fans. Okay. Announcements for today. Just a couple. Hand in homework number 3. That's due tomorrow in lab. So some of you have indicated to me that you're having a little trouble getting those box plots constructed, the side-by-side box plots. And I'll show you how to do that today in class. Just making sure to learn to check that box to display those outliers. But I'll show you that in just a minute. Online homework, you have a Chapter 4 assignment that is available and due this Friday at midnight. And then again, you have an exam coming up, and we've been putting these announcements up there. Plan ahead, but do let me know if you feel like you have a conflict that cannot be rescheduled. And then I just want to kind of get you thinking about what kind of device you want to bring with you to the exam. So I'm well aware that there are lots of apps out there that mimic a calculator, and I love that. But unfortunately, we just cannot let you bring a phone into the classroom. So, you can have your phone, you can have it off in your backpack. I'll say more about that as the time gets closer. But just be planning ahead for what calculator you're going to use and making sure you're familiar with that calculator. And then just lastly, a reminder that study jam session is occurring every Monday and Wednesday from 6:30 to 9. So a nice place to go and work with other students, and then also get some help if you need that. Okay. All right. So let's go back to this David Ortiz question, and just looking here. Okay, so let's go ahead. We'll stop that one. If you want to go ahead and get your answer in, and then we'll look at that. Okay, so this is like, oh my goodness, it gives you just a really absurd number of options. Oh, but look, some of you either Googled it or did know that he just hit 36 home runs yesterday, and so this is his last season, and so a lot of people are paying attention to how many home runs he's going to get this season. So we're at 36 so far, and we're going to look at some more home run data today. So I just thought that would be a nice jump into what we're doing today, comparing different distributions. All right, and so I want you to, just as a little refresher, we've been talking about IQR and how that's a really nice measure of spread. And so here is a distribution of humerus lengths for some Stat 216 students this fall. So this is many of you, humerus lengths. And so which of the following, okay, I'm not asking you to try and make, a distinct calculation, but which of those options would be a reasonable IQR based on what you know about what the IQR looks like? Okay, so I'll leave that histogram up there for those of you who don't have a device and just want to try and estimate the IQR for yourselves. But I'll give you about 20 seconds. Talk about it with a neighbor. so I just want to ask you and urge you to reconsider what you've told me and look at a couple of things for me. So notice that there are 285 students in this data set, and notice the frequency on that graph so that what that middle bar is actually representing, right? Approximately probably around 85 students. And remind yourself what the IQR is, right? It's the interquartile range of the middle, right? Or it's the range, it's the range of this middle 50% of the distribution. Okay, so take that into consideration and decide whether or not you want to switch your answer. Okay, and then we'll reveal the answer in about 20 seconds, okay? All right, so I'm going to stop that one. And I'll show the results. And this is, largely just so that we can really learn together and think about, what's going on with these problems. And so it looks like we have, did I show you all there we go. So looks like we're kind of split between A and B, and then some of you chose D. So I want to say a little bit about each one. So A, I can certainly understand why you would choose B, but let's just look here. Okay, it turns out that if you look at these counts here, it's more reasonable to think that the middle 50% of the data, right, are right in between around this area based on the heights there. Okay, when you're looking at, there's only 285 students here, right? So thinking about, well, what's half of that, 50% of those students, okay, versus between 25 and 40, which would be an IQR of the range, the range of the distribution between these two would be 15, okay, and that would be much more than 50% of the distribution. So that's why A is the correct answer. All right, but then I also want to explain D, okay, so 29 to 34, 29 is the first quartile, not that you could calculate that exactly just from looking at this histogram, but 29 is Q1, 34 is Q3, but remember that when we report the IQR, we report it as a single value, okay, it's not, we could say that the middle 50% of the distribution ranged from 29 to 34 centimeters, right? But when we're using it as a measure of spread, it's a single value, and that would be 5 centimeters is the IQR. Okay? All right. Let's go ahead and jump right into the notes and finish looking at that Michelson experiment and comparing those two, the speed of light estimates from the two experiments. Okay. So I'll just remind you, on Monday, we went through this, we have these data on the, right, we started on page 43. These are estimates of the speed of light from an experiment, two different experiments, experiment A and experiment B. They all have 299,000 kilometers per second subtracted from them. This is the actual speed of light, but when Michelson was attempting to estimate that himself, right, then these were the measurements that he got from two different experiments he was doing. And here we had the 5-number summary for each one, so you can verify that those are what you would get using the methods we've discussed in class. And then we have those fences that we calculated, We figured out that 655 is an outlier for experiment A, and we figured out that 950 is an outlier for experiment B. Okay? So one thing that's nice when you're constructing these box plots by hand is to get all of the pertinent information that you need. Okay? So of course we need the 5-number summary, but then if we do have an outlier, we need just a little bit more information. So we have Q1, we said, was 850 for experiment A. The median was 940. The Q3 was 980. We said we had an outlier of 650. Okay? And then we have the smallest value that is not an outlier. Okay, so we did have that outlier of 650. The next smallest value, if we look at our all of our data on page 43, the next smallest value that is not an outlier is 740. Okay, because my lower fence was 655, so that 740 is not an outlier. Okay, and then my largest value, which is not an outlier, is just the maximum, because that maximum value was not an outlier. So I'm just going to put that 1,070. Okay? All right, so that's all the information that I need to construct my box plots. Okay, so we've already done, experiment B has been done for you. And now we're just going to look at how we would find the box plot for experiment A. Smallest value, which is not an outlier, is 740, or excuse me. Yeah, so the smallest value, which is not an outlier, is 740, and then my outlier is 650. So I'm going to draw my outlier at 650. And then I'm going to make my new whisker, so it's not the new minimum, but it's the new minimum of the box and whisker plot, is 740 instead of 650. Okay, so it's still a data value. Okay, we don't plot those, remember, we don't plot the upper or lower fences. Those are just for checking for outliers. Then my Q1 is 850. So my next line that I'm going to draw is going to be at 850. Median is at 940. So again, doing my best to eyeball that. I know it's not going to be perfect when you're drawing it by hand, but please do make an effort to make them nice and neat and to as much scale as possible, making sure when you're creating that y-axis to make these have a nice equal separation on that y-axis, clearly labeling what this is here. Okay, and then the next value of Q3 is 980. So I'm going to do my best to get that 980 in there. Okay, and then lastly we have the largest value, which is not an outlier, and that's 1,070. Okay, so we had a separation here, so we'll just say about right here. Okay, so those are my 5 points. Now all I have to do is connect the 3 middle to make the box, and then draw the line to make those whiskers. Okay. Okay, while I'm here and while I'm remembering to do it, I want to make sure that you know how to do this in StatCrunch. So I'm just going to take a little aside and show this to you in StatCrunch. So these are the data. The speed of light data are the actual observations are the first variable that's being displayed here. Okay, you can see all of those all of those speeds of light. And then we have the we have whether it's experiment A or experiment B. So what I'm going to do, so there are two variables being displayed here, right? In a side-by-side box plot, we have the quantitative variable, and then we have the categorical variable from which those box plots are being separated. Okay, so let's go ahead and check that out. So we have box plot, speed of light. Okay, so I tell StatCrunch I want to look at the speed of light variable, and then I want to group by the experiment variable. Okay, and when I hit compute, it's not, if I don't check this box, then it's not going to check for outliers for me. So you need to make sure when I ask you to do that, check that little box that says use the fences to check for outliers. Otherwise, it's not going to check for those for you, okay? And we also have a little bit of a surprise because I want to make you aware. Remember when I told you when we were dealing with the quartiles, learning about how to calculate those for the even and the odd case? So there are just slightly different methods, and especially when you have smaller data sets, you could have a little bit of a difference. So we're going to see in this one that based on the method that StatCrunch uses, experiment B will not have an outlier. So I just want to warn you, but it's okay. Okay, it's still very useful information, just so you're aware about those different methods. Okay, and so now here are the box plot, the side-by-side box plots. I should rename that to say experiment level, essentially, for that variable 2. Okay, I have my y-axis there, nice, and the label up at the top to tell me what the y-axis is displaying. There's that outlier of 650 down there. Okay, and again, it decided that upper outlier was not an outlier in this case because it was using a different method for finding the quartiles. Okay, but that's it. Okay, so pretty slick, pretty cool that you can create those nice, really straightforward graphs so quickly. Box plots are extremely informative when you want to look at a quantitative variable but separated by a categorical variable where there's 2 or more levels. They're just really nice instead of trying to like eyeball 10 different histograms. You know, looking at these box plots, it's much easier to see the differences in the main features of those distributions. So that's why we like those box plots. Okay. All right. Any questions about that before I go back to the notes and talk about what we're going to be looking for when we compare these box plots? Okay. So yeah, just make sure to copy and paste that right into your document and you'll be all set. Okay. So like I just said, histograms are definitely going to give us a lot more information than a box plot. If I'm just looking at a single distribution, then I want to go ahead and go for the stem and leaf display, the dot plot, or the histogram. Okay? But box plots are awesome for comparing distribution across levels of a categorical variable. Okay? So when we're writing these comparisons, and please take this into account when you're making your comparisons for the homework and the worksheet tomorrow, I want you to kind of star this for yourself and just make sure that you're addressing these 2 main points when you're trying to make a comparison. Okay, first of all, which group tends to have larger or smaller values? And second of all, which group has more variability or larger spread in its values? Okay, so you can note this, a way to do this when you're talking about these tendencies is by noting the medians and the IQRs or the means and the standard deviations respectively. Okay, but when you're wanting to address shape, it's not going to be as easy because you don't have that full distribution to look at like you did with a full histogram. And so you want to be careful about how much you say about the shape of a distribution because there's not a lot you can say, but there are a few things that are worth mentioning, and so I want to talk about those right now. and give you an example of how I would compare these two distributions for the speed of light experiment, or the speed of light experiments. Okay. So like I said on the last page, two most important things. What's the overall tendency that you're seeing? Okay, and what's the difference in the variability between the two distributions? Those are the two main things I want you to address. And please make sure to be comparing them. Don't just list out all the features for experiment A and then list out all the features for experiment B, but never actually make that comparison. Okay, so the first thing, I'm just looking at this, trying to figure out, well, what am I going to say about this graph? And I say, well, definitely experiment A. Not every experiment had a higher estimate, speed of light estimate in experiment A, but overall experiment A tended to have higher estimates, right, than experiment B. And I just want you to tell me that. That's like the biggest thing that's jumping out at me. Okay, and so putting that in the context of the problem and just stating that in your first sentence is definitely the way to go. So let's go ahead and do that for ourselves. So we're just going to say Michelson's speed of light experiment A and you don't want to say that the speed of light experiment always had higher estimates for the speed of light, right? Because that's not the case. So you just want to say tended to higher speed of light estimates than experiment B. I could capitalize that, I guess. But, and then a really nice way to support that is just by saying, you know, with a median of 940 kilometers per second compared to the 810 kilometers per second well, maybe not the would be the taking that out. All right, so I've had more variability as well. A or B. So when I talk about variability, so you could think of ways that we measure variability are IQR and standard deviation, or range if there's not an outlier. So which experiment would you say has a larger IQR? Experiment A, right? And so, yeah, so there's more variability. That's the language we would use in experiment A than there is in experiment B. Okay, so let's go ahead and write that down as well. So experiment A also had more variability in the estimates. Okay, and again, you can support that with an actual number that's measuring that variability. Okay, so you could say, well, we had with an IQR of 130 kilometers per second compared to 55 kilometers per second. Okay. All right, and this kind of brings up a really important point that we're going to address throughout the class, that it's important not to only address the center of a distribution, but that it's quite important to think about how variable those estimates were as well, okay? Because that's really going to make a large distinction when we're trying to make a comparison between those two as a whole, okay? Lastly, if there is really an unusual point or unusual feature, you want to go ahead and stress that as well. So I might want to point out those two outliers, which I'll go ahead and do for us here. Okay, so I'll say experiment A had one low outlier of 650, and just trying to keep those units in there helps to make everything make more sense. And experiment B had a high outlier of 950. Okay. So I've given you the overall comparison, and I've mentioned center and spread, and then also addressed unusual features if I have them. Okay? All right. Any questions about that? All right, so just as a final summary, just remember not to just describe the distribution separately and to really make an effort to make a comparison. And when you have, let's say you have 10 outliers, okay, please don't list them all, okay? Just try and take the most pertinent, interesting information away from the overall picture, but there's no need to list every single thing you can think about from both distributions, okay? So it's an art just trying to make a concise comparison that is still giving you quite a lot of information. All right, so the next thing I want to talk about is just making sure we understand exactly how to compare these box plots. So below are some side-by-side box plots of the June 2013 state unemployment rates grouped by region of country. Okay, so we have the Midwest, we have the Northeast, the South, and the West. Okay, so we have these different regions. And we want to just make sure, just to look at these, make sure that we're on the right track, knowing what exactly we're looking at. Remember, box plots are always going to be displayed. The y-axis always goes from the smallest value to the largest value. Okay, so therefore, this is Q1, the median, Q3, and the max, right? And that's true for every single one. So which one of these had the largest median unemployment rate? The Northeast. Okay, I'm just going to write an abbreviation there so that. Which one had the largest IQR? Midwest, okay. What about the smallest range? Yeah, so some of you might say Northeast, but remember, when we're calculating range, right, the definition is max minus min, so that outlier is still included in that calculation. So South looks to me like it has the smallest range. Remember, the maximum minus the minimum, so we'll just say the South. Okay. Finally, which state had the highest unemployment rate? Okay. All right. That's all we can say about that. And the highest unemployment rate up here, that's the West there. So that's the highest, yeah, the max, yep. All right. All right, so here we have another example. So we have the following data on the number of home runs hit per season with a minimum of 300 plate appearances. So some of these players would get hurt during a season, and so we didn't include them if they didn't have at least 300 plate appearances. And so Babe Ruth has 17 seasons, Hank Aaron 23 seasons, and David Ortiz with 18 seasons. And these are the number of home runs for each of them. And so we want to be able to compare them. All right, so this is a nice small data set so that we can actually visualize what's happening here. And this 29 with that asterisk there, you know, we're going to leave just because everything's been kind of constructed with that 29, but you can put in your head that that's now 36 because he just got another one last night. So we're at 36 for his last season here before he retires. But let's go ahead and look at this side-by-side box plot and figure out what we want to say. Okay. What's the first thing that jumps out at you in your head that you think, okay, I definitely want to address overall picture, who had the most home runs per season on average? Ruth. So Ruth tended to have the most home runs per season, followed by Hank Aaron and David Ortiz. Okay, and then you could cite those medians if you wanted to. Okay, so we'll go ahead and put that together. All right, and then I want to address, if I do see any differences in the variability, I want to address that. You know, when I'm looking at the IQRs of Ruth, Aaron, and Ortiz, I'm not seeing a lot of differences, although, you know, you could make the argument that, Ortiz has just a little bit less variability. But I'm just going to go ahead and say, you know, those IQRs look pretty similar, and then I'm going to point out those two outliers. Okay, so I'm just going to say all distributions have similar IQRs. But Ruth had an outlier of 11 home runs. 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 Ortiz had an outlier of 54 home runs. Okay, so again, just making sure to make that comparison in the context of the problem, writing in complete sentences, all of that good stuff we've been covering, okay? Any questions about that? Okay. All right, so I want to show you something quickly with these Ortiz data. I want to see if I can put this on here so that you can see if I can get this to where it's nice and without a glare. I think that should, trying to figure out, oh, there we go. That looks pretty good. Okay, I just want to show you a couple of things on the calculator. So again, you're not required to have this exact calculator, but this is the most common one that I see in class, and so this is what I make my demonstrations in. And I just want to point out how to find a couple of summary statistics and these instructions are in the notes as well, but just to make you aware that you can be doing these in your calculator. So the first thing that I want to do is I want to be able to enter data into my calculator. So if I hit this stat button, I have a few different options, and the first one is just edit. And that means, can I edit a list? Okay. And if I want to clear out a whole list, I would push clear and then enter, and it would completely erase everything that's in that column there. Okay, but I just, lovingly put all of the Ortiz data in there, and so I don't want to delete those. So we're just going to, 9, 10, 18, 20, you can see that those are all of the data, those home run data for Ortiz, okay? All right, so my data are in there. They're in L1. I want to remember that in case sometimes, this may have gotten renamed somehow, or maybe you're entering the data into L3. That's fine, but you just want to make note of that so that you can tell your calculator to find the summary statistics for the correct column. Okay? Okay, then I'm going to go back to the stat button, and it's going to go back to that original menu. Okay, and I'm going to go over to calc. And so for right now, all we care about is that first option. It's just called 1var stats. Okay, I'm going to push enter. If my data are not in L1, then I'm going to go ahead and say I want it for, whatever. See all these options for the list that you have down here. There's L1, L2, L3. Push the second button and tell it what list you want. So I want L1 because that's where I put that. You don't have to do that if it is in L1. It'll just automatically do it for L1. But I just want to show you how you would do that and push enter. Okay. What do you think X bar means? Mean, yeah, so we've been calling it Y bar, but they call it X bar, so that's fine. The sum of all of the data values is 531. Okay, SX, that is the standard deviation that we've learned how to calculate in class. Okay, so this sigma x, the only difference there is that they're dividing by n instead of n minus 1. Okay, and so we want the SX, dividing by n minus 1. Tells us that there are 18 data values, tells us the min, Q1, median, Q3, and the max. So there's our 5-number summary right there, okay? Just a reminder that, again, this inconsistency with how our technology is calculating the quartiles versus what the textbook and the notes teach us. So for the odd case, this might be a little bit different. So I just want to warn you about that, okay? But, in the real world, it's not, that little difference isn't going to make a difference, okay? So as long as you know what Q1 and Q3 mean, right, in big picture, that's really what we're about, but you should know how to calculate the method, using the method that we've described in class, just for a small data set, okay? Any questions about that? Okay, so just so you know how to get a quick set of summary statistics for yourself. And now I want to talk about what else we can learn from a box plot. So it turns out that if you think about it, box plot, by just taking our big distribution with lots of information and condensing that to 5 data values, we lose a lot of information, right? So those box plots are not going to be able to tell us much about the shape of the distribution, but we can kind of think about what a box plot might look like when we're looking at a histogram. Like, what would that box plot look like for this histogram? But going in the other direction is a lot harder. Taking a box plot and trying to visualize what histogram what distribution could have produced that. There are a lot of things that can go wrong there. So I'm going to try and point that out here right now. So let me just draw corresponding box plots on the bottom of these histograms just by eyeballing them. Okay, we have the minimum. Okay, then we have Q1. Okay, there are a lot of data here, right, based on the height of those bars. So that median is going to be pretty close to Q1. Okay, and as the height goes down, right, it's going to take longer to fill that next 25% of the distribution. So my Q3 might be all the way up here. Okay, and then finally, the remaining 25 component represents 25% of the distribution. Okay, yeah? That's a great question. So the question is, wouldn't that one on the right be an outlier? It very well could be, and then I would adjust that box plot accordingly. But it's not entirely clear. I would say, if I had to guess, that using our 1.5 IQR rule, it might not be an outlier. But it's hard to say. But yeah. So basically what we see here, so we have the min, we have the Q1, we have the median, Q3, and the max. Okay? Skewed left distribution is going to look exactly the same in the opposite direction. Okay? So this one has a little bit more of the distribution. So it might kind of go like this. Okay, so we have the min, we have Q1 again, the median, we have Q3, and we have the max. Okay? All right. Then we have a distribution that is unimodal and symmetric. Okay. Might look something like that. All right, what about the bimodal distribution? Should I draw 2 boxes? No, right? So I might just have a little bit more space in between here. That's probably not entirely perfect, but you get the idea that there might just be, the interquartile range would just be a little bit wider because it takes longer to fill up these, or longer, but you get what I mean, the space in between those is going to be bigger. The take-home message here is that, I'm losing a lot of shape by using a box plot, right? I can't tell if a distribution is going to be bimodal just by looking at the box plot, okay? I can hypothesize if a distribution may be skewed, right? I can't say that this is not a bimodal distribution as well, but this looks like it could be skewed because most of the data are occurring, on the left-hand side of the graph, and then it's kind of spread out on the right. So this would indicate to me that it's likely skewed to the right, but there's no guarantee that there's not bimodality and other things going on there. Similarly here, right? It looks like most of the distribution is kind of bulked up on the right, and then spread out on the left side, indicating a likely skewed left distribution, but certainly that's certainly not a guarantee. So these things, these 3 points down here summarize what you're kind of looking for if you're trying to kind of hypothesize about what distribution may have created your box plot. So if we have right skewed data, Q3, just like this, Q3 is going to be further from the median than Q1. Left skewed data, right, Q1 is going to be further from the median than Q3. For symmetric data, whether it's bimodal, unimodal, right, if they're symmetric, then Q1 and Q3 should be equidistant from that median, okay? All right. So just to kind of get you picturing and learning more about how to look at those box plots and what they're actually telling you, I think is important. Okay, and I've said a little bit about this, and I just want to make just a couple of more points before we finish up here about outliers, okay? So we've looked at a couple of different ways of identifying potential outliers. So visually, just looking for what looks unusual, and then second, using that 1.5 IQR rule to actually define what's an outlier for us. Okay? But then you're probably wondering, well, what if I think that something is just a typo? Is it okay to just remove that? And so it's really important to think about what could be actually contributing to this outlier. And so let's look at a couple of examples, okay? So the first thing to do is to really try and do some research and figure out whether you think that could have been just some type of a typo or whether it's actually a true value, that outlier that seems so unusual. Okay, so we have in our text, we have some tornado data on page 33, on page 33 of the notes. The 553 deaths in 2011 is much larger than for any other year. But we want to know, was it a recording error? Okay, and if we look at the original data, it tells us that it actually was not an error. 2011 was just a really deadly year for tornadoes. However, if we also look in chapter 3, problem 24 of the textbook, and reports another, some tornado deaths as well from 1998 through 2011, you'll notice that there are some discrepancies from our data. For 2002, we have 55 deaths, while problem 24 reports 555 deaths. All right? So one easy way to figure that out, should I be including this in my data set? Well, we can just look it up, right, and figure out which one is correct. And it turns out that the 55 is correct. That 555 was a typo. Okay, so we never remove outliers, but we also want to do some further investigations to make sure that that they're valid to be incorporating into our reports. Okay, so we'll finish up talking about we'll talk about transformations on Friday and get started into chapter 5 with the normal distribution.